Morning, Mike Griffins, video number 7, classification of matter. Looking ahead, this video is going to be slightly longer than the other ones, but we got some important stuff to get through that's going to help us with things for the rest of the year. When you're done, you will be able to classify types of matter as elements, compounds, or mixtures, and draw particle diagrams that represent them. Okay, let's do it. So first, classification of matter, right? Atoms are represented by single spheres. You could color them all in. You could leave them blank in the middle. You could put an X through them. You could put a pattern through them. So each one of those 4 that I put up there, each single particle would represent an atom. And because I labeled it differently, I would be able to assume that the atoms are different, but they were all single atoms. Okay? Molecules of elements are, because of the word elements, are 2 or more of the same size and color spheres joined together. So an element would look like this. This is what we call a diatomic element. Di, 2, atomic, atoms, element. 2 spheres, same color, same shape. Bam. Okay, so we do have things called diatomic elements. I don't want you to be confused and think that this is a compound. It's not a compound. It's 2 of the exact same thing. So oxygen exists this way. Hydrogen, oxygen, fluorine, chlorine, bromine, iodine. And anybody else? Is that? Yeah. Oh, nitrogen. Nitrogen. I know there was an N in there somewhere. Off Pringle is how I remember it. So we'll get into that later. All right. So a compound has got to be molecules of it's got to be represented by 2 or more spheres of different size and color joined together, at least different color. So I didn't do different size in this way in this compound because here's one element linked up to another element. So that's the definition of a compound, more than one element. And we learned in the vocab part where that can be chemically broken down. I can chemically, with some chemical, depending on what this compound is, break that black and the white one apart. Okay, whereas the other one I can't chemically break it really apart. Okay, particle diagrams in general is the picture of the particles and helps us distinguish atoms from molecules. It also will help us look at phase. So first, talking about pure substance. A pure substance, by definition, is the same thing all the way throughout. So I can have a pure compound. A glass of water is a great example. Water is H2O. We all know that. H2, 2 H's, O, 1 oxygen. H2O is water, is what you commonly refer to it as. And you can have a glass of pure water. There's nothing in it. Every compound, H2O, its neighbor compound is H2O. So it's pure. Same all the way throughout. Okay, let's get into drawing some of these things, and this is probably a great lesson to have with you to do the POGIL. If you've already done the POGIL, this thing will make perfect sense. So monatomic element. Element is one color, and then monatomic, mono means one, so only single spheres. So there you go. Single spheres in a box, you got a monatomic element. Diatomic element, on the other hand, is 2 atoms. So 2 atoms of the same color is the important piece, and they're going to come up together because they are linked. All right, notice they are not changing colors. A compound would at least have different colors, if not different colors and size. Okay, so it needs to be a difference in the 2. So here I have a filled in and non-filled in circle representing a compound. But this particular compound is what we call, or whole substance is what we call pure, because each compound's neighbor compound is the exact same thing. Does that make sense? I hope. That's the difference between pure and mixtures. Now let's get into mixtures. Mixture is, just like it sounds, 2 or more things together. Does not look the same throughout. That's specifically a heterogeneous mixture, by the way. So a mixture of compounds. That means 2 different compounds. So I have this compound and I have that compound. You can draw them similar to that, or you can differentiate them in your own way, to be honest with you. As long as 2 of them are the same and 2 of them are the same, but together those 2 different things are different. So you can see that that's how it is here. I have 2 that are the same. I have 2 that are also the same but different than the original 2. A mixture of monatomic elements. Mixture, more than one. Monatomic, not linked by itself, mono. So two different kinds of single elements. There you go. Notice they are not compounds, they are not together. Compounds being together is a big deal. Okay. Good? Good. Now, phases of matter. I can use these particle diagrams to do phases of matter, and this is kind of important, and I want you to listen carefully to why I'm drawing them the way I am, because it gives me a lot of information. So first off, phases of matter is this, they can be solid, liquid, or gas, depending on how much energy is there. And we can always differentiate how we draw their arrangement to let me know what the phase is. Okay. So specifically, solids are going to be the coldest and the most rigid. Liquids, the particles can roll over each other. Gases, the particles are separate and moving in random straight line motion. So I need to take all those things I just said and put them into how I draw the molecules with solids, liquids, and gases. So specifically with solids, I want to make sure they're linked and look very rigid. And notice I don't touch the wall of the container, but I do touch the bottom. If you drop a penny in a cup, boom, penny hits the bottom of the cup. Does the penny touch all the sides of the cup? No. So this lets me know it's a solid. Because that's arranged that way, they're not falling over from itself, and that lets me know that they are rigid and stuck together. So the particles are touching and locked in position. Does not take the shape of the container. That's a science definition. It does not take the volume of the container. So it doesn't conform to whatever is holding it. The opposite is true for the others, but not fully opposite, right? Liquid's only one piece. So let's do it one at a time. So liquids. Generally, the pieces are touching. If I were to draw this on the board, I would draw them a little bit overlapped, though, just to show that they can move. But notice they fill the walls of the container. So if I put water or coffee in my cup, I don't have to fill it all the way up. It doesn't take the volume of my container necessarily. I could put a half a cup of coffee in, but it does take the shape of my container, is what we say. So it's at least going to go from this wall to this wall of the coffee cup, and it's going to fill the entire bottom of the coffee cup first before the volume starts to increase. Okay, so the particles are touching, but they can move. This does not take the shape, or does take the shape of the container, but does not take the volume of the container. Okay, so we changed one of those things from solid to liquid. Gases will change. Make sure both of them are changed, and we'll have gases. So gases, the particles are not touching and free to move. So now the particles are not touching and can move. It does take the shape of the container, and it does take the volume of the container. If you think about the air in the cup or the air in the room, the air takes up every part of the room that it possibly can. It doesn't just stay confined. Where a penny would just sit here, liquid would pour over into whatever was going to contain it. Make sense? Good. And I think we are almost done, but not. Okay, so we have to fill out this little chart, and in the past, this was one of the you-do pieces, but you really kind of got to read it backwards in order to get it. So I see that matter is just stuff, right? The substance, and I can separate between cannot be separated by physical means and can be separated by physical means. That, by definition, is a pure substance and a mixture. Mixtures I can separate by physical means: sand and water, sugar and water. Pure substance, water. I can't just separate water from water, not with an actual technique. I can pour some here and pour some there, but that isn't what we're talking about. How can I physically separate them? Okay. Cannot be separated by chemical means. That is the definition of an element. Where separated by chemical means only is the definition of a compound. So I can draw a particle diagram of an element. We learned how to do that. And I decided to draw a diatomic element here just to reinforce that this is what we call an element, because they're all the same thing. When it's all the same thing, it is not a compound. Each sphere is the same. A compound would have to have different spheres hooked up. So there's a particle diagram of a compound. So we just did the pure substance side. Let's go over and do the mixture side. It says same composition throughout. Well, same is homo. So homogeneous is the same throughout. Different is hetero. Heterogeneous. And I know you've heard of the prefixes homo and hetero. Think about where you've heard those before. Homo means same, hetero means different. Think. Okay. Particle diagram for homogeneous. I put in the liquid here, and as I Stir in my sugar, guess what happens? As I stir sugar in, it dissolves and it looks the same throughout. So that's a homogeneous mixture. There's two different things in there, and now it looks the same. Heterogeneous is a little bit different. So if I take two things and I put it in the water, one dissolves and one doesn't. The stuff that doesn't dissolve generally falls to the bottom. So one piece dissolves, one doesn't. I can see two different things now. I can see the liquid and I can see the sand, or I can see the coffee grounds, or I can see whatever it was that's solid that didn't come down. Italian dressing is a great example of a heterogeneous mixture. Yeah, even if you shake it up and make it all over the place, you can still see the red pieces, little green pieces, little darker black pieces that are the different spices within the dressing. I can see more than one thing. It's heterogeneous. Fair? Fair. And I think that maybe number 7. So good luck drawing your particle diagrams. I check your work with my work and we're all set. 2.